I'm going to get the entire office, but I'm sorry, where am I? Fridays.
All right. Good afternoon, everyone. Thanks for joining us today. So today I'm very honored and excited to have Dr. Abhijeet Borkar here. Who got his PhD at the University of Cologne. He's also affiliated with the National Institute for Radio Astronomy. And he's going to be doing a postdoc in Prague, where I met him. So that's the Astronomical Institute of Czech Academy of Sciences. Now he's permanent staff there, where he has duties also for one of the nodes of the Regional Center of the European Network. So thank you for joining us today.
Thank you so much for having me here. I'm really excited to visit Green Line Observatory. It has been a long time coming for me. I have planned to visit here, and today I'm happy to give a short talk discussing what I work on. And a lot of the work that I will present today is a collaboration between a lot of people who were formerly or currently associated with Prague and Warsaw. Some of the people have already left Prague, as you can see, and he is not working here. But many people who are associated with our groups, a lot of the work is done in collaboration with them. So let me just give you a short introduction to myself. So most of you don't know me. So I was born and brought up in Pune. Some of you know my closest place because it's the home of GMRT, one of the radio telescopes, the big radio telescopes in the world. I did my bachelor's and master's from Pune University, and then moved to Germany for doing my PhD, where I was part of the National Max Planck Research School at Cologne and Bonn. And then after that, I got a postdoc position in Prague, and for the last 7 years, I have been working on. In Prague, I primarily work as ALMA support scientist, and in the spare time I get from that, I study as AGN student. As an ALMA user support scientist, I do quite a lot of different things. A lot of it is technical in terms of helping users preparing observation proposals, the phase 2 observations, and then doing quality assurance. So in the past, I was doing quite a lot of manual calibration and imaging. Now I'm more working in pipeline and development. And also what we're doing is developing quite a lot of high-level data products with ALMA, and also developing analysis scripts for ALMA analysis. Along with that, we also do plenty of non-technical stuff, including conference and workshop organization. So basically, we have had 2 years of conference that was aimed towards early career scientists, so young astronomers who did not have the opportunity to present their work during the pandemic. So we had a very successful 2 years of conference organization where all users of ALMA from all over the world could present their work. Along with that, we do quite a lot of student training, lectures, and other stuff also. Here is some stuff that I will not be talking about today. So if you want to discuss about these things with me, you're welcome to talk to me about that. So one of the things that the first few objects are from our ALMA high-level data products initiative, which is using the archival data that is present in the ALMA archive. We are developing tools, techniques, as well as products where you will have a much easier access to the data, and you don't have to download individual project data sets and figure out what's present, what's not observed, so on and so forth. So the first one is already published recently, which is looking at the millimeter counterparts of SDSS detected quasars, so which is partly a region of frequency which has not been studied too much. So this was one of the first catalogs that has been created for sub-millimeter wavelength for quasars. And the second thing that is hopefully should be finishing in the next 2-3 months is ALMA view of the galactic center, where we are collating all those molecules that have been observed with ALMA, looking towards the galactic center region and combining all of those data sets together to bring them in single webpage. So you can have a quick view of what's been observed, what the data look like, and then you can decide what to do with the data sets. Along with that, there are a couple of projects that we have been working on. One of them is kind of relevant to Green Bank because we are looking at some archival data that we might be using in the future. So we're looking at highly star-forming galaxies, and we are trying to see whether they show any alien signatures in that. And the other one that I'm working on with my bachelor student is the fundamental way of accretion revisited, where we are trying to modernize the relation that was developed earlier in 21st century, so in 2003. But yeah, so we are trying to sort of review that analysis and improve it with modern data sets. So if you ever want to talk about any of these topics or something related to this, I am available tomorrow, or you can just contact me by email. So with that over, let's talk about black holes. There are two primary types of black holes that we know of. First is the stellar mass black holes, which are usually the size of mass of the sun, few times mass of the sun, to maximum we have detected so far like few tens, so 18, 19 solar masses. And then the other ones are supermassive black holes, which are sitting at the centers of most galaxies. They tend to be ranging from few million to few billion solar masses and are responsible for a lot of activity in the universe. So there are these two different types of black holes. There are, of course, intermediate mass black holes, which haven't been detected yet. There are quite a lot of candidates, but there are no confirmations of those, which lie between 100 solar masses to a few million solar masses. And then there are also primordial black holes, which haven't theorized, but nobody has detected them. And these black holes are quite simple. So, as some of you might know, black holes can be described by simple three parameters. You just have to look at black hole mass, its spin, and charge. That's it. That describes everything about black holes. So they're really simple, and that sort of raises the question: are all of these black holes which span a wide range of masses, are they similar completely in the sense that does the physics work the same for all of these black holes? And especially, this physics might work same once you're very close to the black hole or inside the event horizon, but this also works similarly when we are looking at slightly outside of the black hole also. And for most of the black holes, you don't really have to worry about the charge. Charge, electrostatic charge is not relevant on astrophysical scales. So what people mostly care about is mass and spin. And what we will be discussing today, the spin also doesn't play too much of a role, or it plays indirect roles, so we will also ignore that. So today's question is essentially, does black hole mass matter in terms of different physics, or is the physics same across entire black hole mass scale? So we have seen detections of black holes in stellar mass case through gravitational wave discoveries, and now there is dozens and dozens of candidates present with the LIGO detections. But traditionally, the way we used to look at stellar mass black holes in what are known as galactic black holes or X-ray binary systems. So these are called galactic black holes primarily because they are quite faint in comparison, and you don't detect them much further outside of the local nuclear system. So these black holes are stellar mass black holes in a binary system where one of the stars has gone off and has become a compact object. So usually the compact object would be a white dwarf, a neutron star, or a black hole. And for our case, we will just discuss the case where the compact object is black hole, and it's already another star, which is either a main sequence star or an evolved star. And what happens is that because of the gravitational attraction between the two objects, a lot of the atmosphere of the companion star that gets pulled in towards the black hole, and that creates this nice accretion disk around it, and that is very bright, several millions of Kelvin in temperature, and that emits most of its light in X-rays. So these objects are visible often primarily in X-rays, so they are called X-ray binaries. And what is often also associated with these systems is a launch of relativistic jet, so a large amount of radio emission that is coming from these jets that you can also detect simultaneously along with the X-ray observations. So this is kind of a very nice system that we detect. And people have studied the accretion around these stellar mass black holes, and because these are nearby black holes within our own Milky Way, we can observe them with good precision and also with good cadence. So we can observe them multiple times over the entire accretion cycle. Usually, this accretion is described in two different modes. So you have the high accretion mode when there is a lot of material present. So you have the high accretion mode where the accretion is close to the Eddington limit, where you have a lot of material flowing in, and the thermal disk, so the accretion disk is optically thick. So essentially it's very dense and very slim, geometrically very slim. So in that case, the accretion is very smooth and leads to very strong emission in X-rays for these black holes. While on the other case, if there is not enough material present, the accretion then turns into a low accretion mode where the efficiency is much smaller, so less than 1% of the electric limit. And the flow turns into a what is known as advection dominated accretion flow, where on the outskirts you have a nice thin accretion disk, but towards close to the event horizon of the black hole, you get a more perfect disk, which is optically thin, so it's not dense. And this kind of accretion is less orderly and has effects because of magnetic field and other issues. It also leads to launching of the radio jets. And this is kind of reflected in the spectrum that you see. So this is a cartoon version of the X-ray spectrum that you can see from these sources. So on the left side is the high Fox state when the object is accreting at a very high efficiency. And what you get in yellow here is the accretion disk, which is a simple black body radiation. So you get a nice black body curve there. And the hard emission is very low and it's seen as primarily as power law emission. So on the other hand, when it goes into low efficiency mode, what you get is that the accretion disk becomes less prominent because it's not accreting efficiently. But you get emission what is known as the corona, which is, we don't know exactly where the corona sits. That is sort of unknown mystery itself. But we see its effect in terms of the power law emission in hard X-rays. So because most of the emission in that case comes from hard X-rays, it's called a low hard state, where the efficiency is low, there's low luminosity, and it's the spectrum is hard. While this one is called high soft state because the peak of the emission for the accretion disk happens in soft X-rays. So you have a nice accretion disk visible and you don't get too much emission in the hard X-ray. And then you can calculate this parameter called hardness, which is the ratio of the hard luminosity compared to the total luminosity. And it's related to the sort of total power law luminosity and disk luminosity together. So this is kind of the basic way of understanding different accretion modes for these black holes. And this sort of is parameterized in a very nice, what is known as the Q-shaped diagram or turtle head diagram, where X-ray binary will start somewhere here when it's not accreting anything, it's not doing anything. It starts at the bottom right part here when it's at quiescence. And what happens is that it starts accreting material from its confinement star. It has a very low efficiency accretion because there's not enough material still pulled in. So it starts with the low hard state. And in that state, because of the magnetic fields, it also launches a radio jet. So you see simultaneously radio emission present in these systems. And as it starts pulling in more and more material, it becomes more efficient and it rises in its luminosity, so it becomes brighter. And as it gets brighter, the radio emission also becomes full prominent. So you will see a launch of a full jet at that point. And as it becomes more and more efficient, you can lead to two different outcomes. One is that the incoming material will stop incoming and it might just fall back to quiescence, and that's considered a failed outburst. But in many cases, what will happen is that the material flowing in will start becoming efficient and will get to the efficient accretion state, where on the bottom, top left part, it will go to the high soft state, where the radio emission stops being emitted, and you sometimes see emission in terms of some small blobs of radio emitted or some leftover radiation from the past, but there is no longer new radio emission happening. And then the system can spend some time sort of moving around in that top left corner, and then eventually, as the material stops coming in, it goes back down to quiescence. So this is kind of this diagram is known as the hardness intensity diagram, where essentially the intensity is the luminosity, and you have the hardness on the x-axis. And this has been well studied with many different sources, and in practice, it doesn't look that pretty. It looks like this, where you have a system that starts somewhere around on the bottom right part of the plot, and then it goes in and so there's a Q shape, and it can spend some time on the top left part and eventually goes back down. So this is kind of a very well studied phenomenon for X-ray findings. And what we wanted to study in this project was, are supermassive black holes similar in that sense with stellar mass black holes? Do they also show this kind of accretion behavior compared to the stellar mass black holes? So are they just same black holes accreting in the same manner, just scaled up at different masses? And the motivation for that also comes from this fundamental claim of black hole accretion that I mentioned earlier today, which is essentially a relation that is correlating the radial luminosity of the black hole and its spectral luminosity and black hole mass. So when you combine these three parameters together, black holes of different masses seem to lie in a very tight correlation. So on the bottom left of this plot, you see all of the black points, which are all stellar mass black holes. And on the top right are all quasars. So these are high mass black holes with billions of solar masses present, and they are accreting very efficiently. They are very bright sources, some of the brightest sources in the universe. And in the middle, you have Sagittarius A*, which is one of the lowest accreting source, also very low mass black hole. It's 4 times 10 to the 6 solar mass black hole, and a lot of much more of other supermassive black holes present in the middle there. So with such a massive mass range, so 10 to the 9 in its in that range, you have such a tight correlation with these properties. So that gives you a motivation that, okay, there must be something going on that is very similar when it comes to black holes, regardless of what the mass is. But there is a difficulty in comparing this easily. The direct comparison is not easy because the accretion disk for supermassive black hole is just physically larger. So it starts much further away from the event horizon, and also it's physically much more spread apart. So it doesn't peak in the soft X-rays as you saw in the case of X-ray findings, but it peaks in the ultraviolet because it's bigger and also at lower temperatures. So the temperatures are only up to 10 to the 14 to 5 Kelvin rather than billions of Kelvin. The other issue is that the timescales for the changes that you saw that I mentioned in the harness intensity diagram. If you just extrapolate what happens for stellar mass black holes in a few hundred days or so, and if you extrapolate that for black hole masses for supermassive black holes, it would take about 100,000 years to a few million years. So it's really difficult to get that kind of evolution seen for individual sources. So what you have to do is actually work with a large sample of sources and then see in aggregate statistically, do we see similarities between the overall properties of black holes or not. The other issue with the emission being in UV band is that there are not many very good quality UV telescopes. So measuring UV data is also quite difficult. There are a lot more X-ray telescopes which have very good cadence and data quality. In that comparison, getting the UV emission is slightly difficult. The other issue also is that compared to stellar mass black holes, supermassive black holes also have to worry about their host galaxy, and we will discuss about that in the second half of this talk. But the problem with that is that the host galaxy has a lot of star formation, which also peaks in ultraviolet. So you have to worry about how much of the emission that you're detecting in UV comes from the host galaxy, and how much of it is coming from the black holes. So all of these things complicate the situation. And the other small calculation that we have to do is, because the AGN masses are spanning quite a large range, you have to use Eddington ratio instead of luminosity. So with stellar mass black holes, you could just ignore black hole mass because we know that it's between 10 or 50 solar masses, so it's within factor of 2 to 5. That's not a big deal. But here you have to worry about 3 to 4 orders of magnitude difference in the black hole masses, so you have to take into account how accurate are your black hole mass measurements and how much does that affect your calculations. But we did that analysis for a sample of sources selected from the XMM Newton satellite serendipitous survey, as well as the BATS survey, which is a smaller survey that has been collected from the BATS instrument on the telescope. So combine this, so the difference is that most of the external sources that we have, these are all quasars and higher luminosity sources that are much further away from us and also are accreting more efficiently. In comparison, the bass sources are mostly local sources, so within redshift of 0.5 or so. And these are also a lot low luminosity sources. And what you can see is that the structure of the plot is quite similar to what we have seen in X-ray binaries. So this is a combined highness intensity plot for few dozens of X-ray binaries. And when you compare that with what we see for AGN, it looks practically identical. And that gives you an idea that the accretion in AGN and X-ray binaries is quite similar. They do seem to have very similar structure and similar processes that are happening there. So we wanted to look at much more in detail. There are different AGN types. So AGN are classified there is a large morphology of and nomenclature similar to most of the botanists will be happy with looking at that. There are different kinds of AGN. So we want to look at if these different properties are also related to the accretion states that we see. So the first thing that we wanted to see are if the radio properties of these AGN are correlated with the accretion state. And as I mentioned previously, that in the case of X-ray binaries, you see this launch of radio jet when the outburst is starting. And when we compare that with our sample, what you're seeing here is the same data that I showed in the previous plot, but with now with color bars showcasing the radio loudness, which is essentially the radio luminosity. And you can see that most of the radio loudness sources are located at the top right, and other radio hard sources are also mostly located on the right side. So essentially also where we expect most of the radio emission to be detected. And most of the sources on the top left part are radio quiet, so they don't show much radio emission. So this is quite consistent with what we also see with X-ray binaries, that only when the sources are in the hard state is when you see radio emission. And once the sources start moving towards the soft state, you stop seeing radio emission. But along with that, this work that was done by Emily during her time in God was to actually look at the radio morphology. So radio AGN are often divided into two classes, the FR1 and FR2 type, which is essentially how the jet of those sources looks like. FR1 is when you see the inner part of the jet very prominently, while FR2s are when you have the outer parts of the extended lobes which are visible. So in that case, the jet looks much more evolved compared to FR1 type, when the jet looks to be much younger. And what you see in this plot is that the FR1s and FR2s seem to be occupying slightly different position in the hardness intensity diagram. And here, one thing that we haven't done is subtract the post-galaxy contribution to our the calculation. So once you do the calculation, these sources will all move down here. So what you see here clearly is that you have FR1 types somewhere around bottom right. And then on the top right part, you will see FR2 sources. So this is also consistent with what you see in the case of X-ray binaries, where you see the jet being launched when the outburst starts, and then the jet evolves as the outburst keeps going. So this is my sort of a cartoon plot showcasing exactly how the radio properties are related with the hardness intensity diagram. Essentially, the FR1 sources are at the bottom right, where the outburst is just starting off. And as you move in the sequence, you get to what are known as radial out quasars, or highly accreting radio sources, and eventually go into the quasar mode, where essentially there is not much radio emission, and you're seeing primarily soft emission coming from the accretion disk. And yeah, as I mentioned, this is very consistent with what we see in the case of X-ray binaries. The other thing that we wanted to see was whether it's sequence classification. So this is the optical classification, and depending on the unification model of AGN, in which it is posited that essentially the sequence classification you see is purely dependent on the orientation of the source towards you. So you look at AGN and it's surrounded by some obscuration. And if you look at the AGN from a top-down view, then you will see the emission lines. And if you see it from the edge-on view, you will not see certain emission lines. So that's how the sequence classification works. So sequence ones are when you see the emission lines, and sequence twos are when you don't see emission lines. And what we get is kind of consistent with that, in a sense that the sequence ones and sequence twos are all gray objects, and they are spread all over, so they don't seem to show any correlation with the accretion state. So the sequence classification in terms of sequence one and sequence two does not seem to show any direct correlation with accretion, but it seems to be more related to the orientation effect of the black hole. But what we see are these three different categories of sources. So the intermediate ones are the sequence classes, which are between sequence 1 and sequence 2. So these are sequence 1.2, 1.5, 1.8, and 1.9. So these are different levels of obscuration, but they also seem to be somehow related to the change in the accretion state. So these all seem to be at the location in the top right part of the diagram, where you are transitioning from the hard state to the soft state. So it seems like that the intermediate sequence type could be related to the state transition in these sources. Also, what we see are these liners, which are low ionization radio AGN, which are low luminosity and also are usually associated with radio jets. And these are all also lined in the very hard part of the diagram. And narrow line sequence ones, which are usually very highly accreting sources. And they also show very high luminosity, and they also, some of these are also very soft in the top left corner. So these kind of sources, these classifications seem to be associated with the accretion state change, while the basic sequence 1 and sequence 2 classification does not seem to be associated with accretion state change. And this has been also corroborated by others who have done similar analysis, but with using different methodology. And they also see somewhat similar structure where the sequence 1 and sequence 2 seem to be more or less occupying the same area, with the intermediates lying between them somewhere, and the liners followed by so very hard part of the diagram. They do have some differences in how they calculate these things. So their sequence 1 and sequence 2 classification seems like dichotomy, but when you account for those effects of the infrared classification, then it's kind of consistent with what we also see. And the other thing that we wanted to see is whether the whole galaxy of these black holes have any effect, or whether we see any correlation between the AGN and the host galaxy. And what you're seeing here is the color is actually the star formation in these host galaxies. And from the histogram and also in the plot, you can see that as you go towards the softer and softer parts of on the top left part of the plot, most of the galaxies are also forming a lot of stars. While when you are at the bottom right part, there is not much star formation happening. And what we can conclude from this is that essentially there is the same amount of gas available for both star formation as well as for accretion onto the black hole. And this sort of evolution is happening together, where the black hole is accreting the gas and growing at the same time. The galaxies are also converting the whole molecular gas into a lot of stars. And not only what we see here is a direct correlation, what we also see is a redshift evolution of this relation. So here we have divided the entire catalog into different redshift bands, and what we see is that as you go higher and higher at redshift, the star formation rate increases and the hardness decreases. So essentially, our sources become softer and softer, so they are accreting efficiently. And as you go come towards the current time, so redshift 0, sources become harder and harder. And this is kind of sort of explained by the cosmological evolution of black hole accretion, as well as the evolution of star formation rate in the universe, where both of these things, the AGN activity as well as star formation rate, peaked in the period between redshift 1 and 3. That's where both the AGN activity and star formation rate has the maximum efficiency. And nowadays, the universe is sort of going towards the down, and there's not much star formation happening, and there are not many highly accreting black holes also present in the nearby universe. So this shows you that essentially the host galaxy and black hole are evolving together, and there is a relation between them, there is a co-evolution between them. Then the question arises is, so how does the black hole influence the host galaxy? So this is kind of coming into the second part of my talk where we will discuss what is known as AGN feedback. So essentially, how does the black hole interact with the galaxy? And as we saw in the first part, a lot of the accretion is happening very close to the event horizon. So this is milliparsec scale. So few gravitational radii use several, maybe 10,000 of gravitational radii, while the galaxy is tens of kiloparsecs in size. So how does the black hole know what is happening in the entirety of the galaxy? And how does the influence go between the galaxy and the black hole? And what we know from observations is, and also from simulations, is that this AGN feedback, where the radiation coming from these black holes, is quite important for galaxy evolution. What is known from simulations is that if you try to incorporate presence of AGN in the galaxy evolution course, and you don't put in the AGN feedback, so essentially amount of radiation that is dumped by the AGN into the galaxy, then you don't form the same kind of galaxies in the universe as we see in the observations. So you generate too many massive galaxies and you don't generate enough small galaxies. So that becomes a problem. So, but once you account for the AGN feedback, even in the simulations, you start seeing that you get the same kind of galaxy profiles that you also get from observations. What is also known is that this kind of AGN feedback is ubiquitous, so it has been seen in all wavelengths. So I was present last week at a conference on AGN winds and feedback, and you saw talks from X-ray winds, optical, infrared, radio. You see interaction between the AGN outflows and winds and radiation with the galaxy in all wavelengths, but also it's observed at all scales. So from very microscopic scales, so essentially few gravitational radii up to the scales of galaxy clusters. So 10 orders of magnitude or even more. And the effect of this AGN feedback can be to either trigger star formation. So sometimes with radiation or radio jets, you can create compression and shock waves, and those shock waves lead to formation of coal and gas clumps, and that leads to star formation in the host galaxy. Or often what happens is that the radiation and the jets essentially dump so much energy into the system that the gas cannot cool down to form these molecular clumps. It's sort of heated up in different ways, or it can be mechanically pushed back. And that way it stops star formation from happening and sort of keeps the galaxy not active. So this way, the effect of the AGN feedback can be both positive and negative. And we usually discuss the AGN feedback in two different forms. One is the mechanical feedback, where you're looking at a physical feedback given by the material that is pushed out by the AGN. So this is in the form of radio jets, but also outflows in terms of winds of different forms from the central black hole. And the effect of it is that it pushes the gas further and further away from the AGN, but it can also lead to pushing the gas completely outside the galaxy and keeping it up. And the radiative feedback is more in the form of sort of quasar wind scenario, where it's the high energy radiation coming from the black hole that imparts a lot of radiation on the surrounding gas, and that heats it up and mechanically it receives a lot of heat energy, its temperature rises, and the gas is moving too fast, it does not clump together and sort of moves away from the gravitational attraction of the black hole. And this kind of symbiotic relation has been exemplified by what is known as the M sigma relation, where mass of the black hole and various different galaxy properties are seen to be very tightly correlated. So here is the sigma, which is the velocity dispersion of the stars in the galaxy. But you can also look at galaxy stellar mass or the mass of the bulge in the galaxy, and all of these properties are very tightly correlated with the black hole mass. So that also tells you that essentially there is a very strong relation between just what is happening at the very center of the AGN system and at the larger scales that we observe these days. And the effect of it is often seen in the case of radio jets, where you have these massive jets that punch a hole through the gas in the surrounding of the galaxy. So these are two examples where you see a radio jet in red here, and this is not direction of the jet, but this is the X-ray image in both. So here you know and purple in the right picture, where you see these massive holes formed in layer. So here is one image, one hole in the form of cavity, and on the right side, you also see these big holes which are present. So there's the inner cavity and outer cavity present in the Perseus cluster. So these are formed by the radio jets which have punched holes through the system that cause the material to be pushed away, and then that hole is then filled by very hot gas. So one of the things that we want to do with Greenland is to actually observe these structures in radio and try to see whether we can measure the effect of these AGN feedback with these sources. But in general, what we want to study is that how does the black hole continue to get bigger and continue to have these massive jets when there is such a strong feedback present. So one of the main things is that these radio jets that you see, these are very massive. So they span several tens of kiloparsecs, sometimes up to megaparsecs. So to launch that kind of jet and to have it active for such a long time, they last for several thousands to millions of years. So how does the black hole keep on getting more and more material when it's emitting so much radiation that should be pushing it away? So how do you keep on feeding the black hole when we have such a strong radiation and energetic feedback? So to study that, we wanted to look at the nearest radio source in our local neighborhood. So this is the Centaurus A galaxy, and this is one of the prototypical radio galaxies. So it's the nearest radio galaxy in our neighborhood. It's barely 4 megaparsecs away, so just backyard of a Milky Way. And it's a low luminosity agent, so it's accreting at very low efficiency. And it has a moderate size black hole with what has been seen in this galaxy is a very mix of structures. So here is a combined image from optical, radio, and X-rays, where you see the optical galaxy in the form of this spherical elliptical blob, and through that is a massive layer of dust present, which is from a merger that happened some time ago in this galaxy that has brought in quite a lot of gas and dust in the system. And from here, from the center, AGN, you see a massive jet that is being launched. So the bluer parts are X-rays, and on top you see is the radio emission from the jet. And on the other side, you see on the bottom right, a counter jet and a bubble formed there. And what's also been observed is that gas is present in the system in various different phases. So there's hot gas in the form of X-ray emitting plasma. You have warm gas, and also a lot of cold molecular gas has been used. And this galaxy is also one that I really like to show in both teaching and outreach talks, because it also exemplifies what are the advantages of looking at different wavelengths. So if you just focus on one wavelength, you will see only one thing for this source. But when you look at all different wavelengths, you see a completely different structure. And only when you get all of these things, you get a full picture of what's going on in the system. So I will not go into the details of this, but essentially what we wanted to study is how does the radiation coming from this galaxy. So we did not want to look at how does the jet interact with the surrounding gas, but how does the radiation that is coming from the system interact with the surrounding medium, because the main thing we want to address is the jet is launched in the perpendicular direction to the incoming material. So that will not have too much effect on what is coming from sort of edge on view. But what does occur in the surrounding gas is the radiation that has been spreading in the sort of horizontal direction. So what we did is we performed some simulations from using the software called Cloudy, where you can set up a system where you have a central radiating source present and a cloud of gas with certain specific properties, so density and mass and so on, few other things, and you allow for the radiation from the central source to be launched onto that gas cloud, and you study the evolution of this cloud to see how the radiation affects the presence of different structures there. And the evolution is then studied by this parameter called ionization parameter, and it's essentially a ratio of the external pressure to the internal pressure of the system. So the external pressure comes from the luminosity from the black hole as well as if there are any stars forming in that system. So in many other cases, you not only have to take into account the radiation from black hole, but there is also nuclear stellar cluster that you have to worry about. For Centaurus A, thankfully, you don't have to worry about that. All you have to worry about is what is the radiation coming from the central black hole and how much is the gas pressure inside the gas. And when you study that, what you get is this nice plot. So I will explain what's going on in this plot because it's not that easy. But essentially, what we have done is we plotted the evolution of this cloud with two different models. One is the red model, which consists of the gas cloud, which has no dust. And the blue cloud is the one which has some dust in it. And the dust has significant effect on how the gas cloud evolves. So the way to read this plot is that if the curve has positive structure, positive slope, then the gas cloud has a stability in the ionization versus temperature scale. And when you have a negative slope, as you see, then you have instabilities present. And that is when you can create a system where essentially what you get from here is you have on top right there where gas is present at 10 to the 8 Kelvin temperature. So this is the maximum temperatures you can reach before essentially you start getting inverse Compton effect and further things. So essentially all the X-ray emitting plasma is present at that temperatures. But simultaneously at the same value of ionization time, that you get a narrow range where you also have presence of Born gas. And so essentially what you have created here is a system where you have two different phases of gas present in the same location and the same kind of radiation zone, but they are present at two different temperatures. And if you include the dust, what you see is that up to a certain point, you can also have certain dust present, even when there is such strong amount of radiation. But without dust, the overall temperature sort of plateaus at 10 to the 4 Kelvin. So essentially, the gas doesn't cool down if there is no dust. But if you include the dust in your model, then after you move the gas away up to a certain point, then the gas is able to cool down and fall down to the temperatures where whole molecular gas can fall. And this is also what we see in the case when we plot the density versus radius. And when you see the yellow color on the top left part of the plot there, is where you start seeing more and more cold molecular gas present. So essentially, only when you reach up to a radius of 50 to 80 parsecs is when you start seeing cold molecular gas. And inside that, you don't have too much dusty cold molecular gas present. And outside, you start seeing it. And this is what we see in observation. So here is a combined image from X-ray, and on top of it are contours from ALMA showcasing where the CO molecular gas is present. So as you can see here, this is the the X-ray emission coming from center of the AGN, and it's completely surrounded by the molecular gas. So there is not much molecular gas present in the core here, and surrounding it, you have the circumnuclear ring that contains a lot of large molecular gas. And you can see it clearly here where there is a big hole in CO, and there is a nice dome around it that showcases where the molecular gas is present. And so this shows how the sort of AGN feedback is pushing some of the material away while keeping hot gas surrounding it. But as I mentioned in the plot with the structure here, is that you can still get some clumps of polar gas with dust present when there is also hot plasma present. And that is also you see in the right-hand side plot here, which showcases the HCl molecular presence in the center. So this molecule is trace of a very dense gas, also very cold, dusty gas. So here you see that even though there is a cold HCl molecules, there is still presence of this small clumps of gas present. So essentially what this showcases you is that the interaction between the radiation creates this multi-phase medium where you have presence of hot plasma, but within that you can form these small clumps which are still present, and those clumps will eventually dissolve and sort of disintegrate and fall towards accretion disk and keep on feeding the black hole. So essentially, there is a large amount of cold gas present in the outskirts, but some of it can fall through towards the central accretion disk and keep on feeding the black hole. So this is sort of very nice interaction between AGN and the sort of surrounding medium that allows it to keep on growing and keep on feeding at a low efficiency, so that it is able to keep launching massive jets for a very long time. So that's kind of what I wanted to show you. So the main take-home message is that essentially supermassive black holes are just stellar mass black holes but scaled up. There are not too many differences in the accretion that you see between stellar mass black holes and supermassive black holes. What you see is that the different AGN classes, so radio classification, optical classification, they somehow are related to different accretion states, except for the sequence 1 and 2 classification, where it doesn't seem to be related to that. And what we also see is that the AGN and the host galaxy are growing and evolving together, and there is a interaction happening between them, where the galaxy evolution and the evolution of the gas within the galaxy is influenced by the feedback that is coming from the AGN. And this kind of feedback leads to this formation of multi-phase medium, where you have the hot and cold gas or hot and warm gas present together, and that keeps on feeding the black hole and drives the gas towards the center, and so leads to accretion, and the black hole can keep continuing growing. But eventually, the material will run out, or the galaxy, the AGN becomes stronger, or there is enough radiation that all the small molecular clusters can get disintegrated, and the black hole will stop accreting, and that's when we get black holes like in the center of Milky Way or other galaxies where they are completely inactive. So that's all from me. And if you want to get in touch with me, you can contact me by email, or if you want to know about my work, you can check out these links here. So, thank you so much.
We have some time for questions.
So you mentioned the AGN's feedback to a galaxy can either suppress or encourage the star formation to increase. And I was wondering, in cases where galaxies are merging, how would that be an example, or what are the driving forces of if within a galaxy merger, what would suppress or drive more star formation?
Yeah, so there are galaxy mergers have really complex systems, so it's really difficult to know exactly what's going on in those systems. But what we see are in the merging systems, the closer they are, the higher is the incidence rate for both star formation as well as for AGN activity. So we see that usually in these merging systems, the AGNs are active, and also there is a lot of star formation happening. So essentially, mergers bring in quite a lot of gas together, and it's also disturbed, and a lot of the momentum from that gas is removed. So for formation of stars, what we need is a lot of the heat and momentum from these atoms and molecules needs to be removed, and so that they can form clumps which will eventually lead to star formation. So that's what we see in merging systems that leads to star formation. And you also have the black holes which are active, so you see signatures of activity there. But what we also see is that they are often surrounded by quite a lot of dusty material that hides a lot of radiation coming from the black hole. So that way, the black hole may not be immediately able to influence the surrounding, but as it starts growing and accreting a lot more material, then it's starts imparting energy in the surrounding system, and that provides a negative feedback. Yeah.
I had a follow-up to that question. You said that so after galaxies merge and then sort of stirs up all the gas and accumulates more, obviously that causes like a lot of heat in the galaxy region. I was wondering what is like the main radiative like cooling process that happens that could eventually prompt star formation?
Yeah, so the main thing is that the momentum and the velocity of these gas clouds, so that has to be removed. So there is a lot of gas present in sort of galaxy arms or in the outer regions, and those need to be sort of removed so that the gas clouds can come together, and the individuals objects may not collide, but the gas clouds also have a lot of collisions, so you can have localized shocks and systems present where that leads to formation of small clouds. There's also a lot of dust that is present because we have star formation happening that creates a lot more supernovae and dust. So then that provides also locations for star formation. So all of these things combined together, we need to get more star formation present in the systems.
I was just curious that a lot image you have CO and HCN. What galaxy is this?
Oh, this is the same Centaurus A.
This is Centaurus A.
Yeah, so
Oh, okay.
this is the dust mine that you see that also actually.
Is it, is there HCl plus?
Yes, there's also HCl plus, HNC and several other ones inside.
I was just curious in terms of the HC and HCl plus ratio, do you know anything? Because a lot of times people, what these infrared get the HCN can get enhanced with infrared. So I'm just wondering about the HCl plus.
I haven't looked at the ratio itself, but it looks quite similar to the HCl map here.
Okay, fair enough.
You said that dustier galaxies gives you more cold gas and more star formation. And then you also showed a nice plot of star formation rate versus age of the
Right.
galaxy. So
Yeah.
were older galaxies dustier, or are those disconnected?
No, so essentially, it seems like the dust forms quite quickly, but what you usually see is that a lot of the early star formation leads to supernovae, and that's what creates higher elements which lead to formation of dust. So a lot of the first and second generation of star formation that led to creation of a lot of dust in the system. So already by redshift of 5, we see quite a lot of dust formation. So most of the sources that we see are still comparatively lower redshift, in the sense that they are redshift 3. But by redshift 5 or 6 already, and when we are looking at the GWST images recently, there's a lot of dust formation even from the first, second generation of stars.
So that wouldn't really come into effect unless you're looking at Z of 5, 6, 7.
Yeah.
Your CO and HCN plots as
Mhm.
well. So the center of the CO, so there's a detection in the very center, yeah, and then there's none, and then there's so is the center, is that more the accretion distance?
No, that might just be some small cloud present in the center.
Okay, let's see. Any other questions? Great, let's thank Abhijeet again.
And I will be here tomorrow also, so if you want to discuss any other projects, then I will discuss that.